Submitting the people I know.
Should I start?
You can start.
So, good afternoon, everyone. My name is Harish Narayanan, and today I'm going to be talking about some recent work that we have done on a goal-oriented error control solver for biomedical flows. And the title points out two key aspects of this work. One is that the numerical methods I'm going to be describing are error controlled, and two, it's that these error control mechanisms are geared towards a specific goal. Now, it's both important and interesting to accurately model biomedical flows because the results from these calculations are used in a variety of purposes. For instance, you can use them to design medical devices. Doctors can use them to plan surgeries. And in some level, they do aid our understanding of healthy and diseased biological functions. So, when I talk about biomedical flows, I could mean one of many things. I could talk about blood flow through the circulatory system. I could be talking about fluid flow through porous tissues, the connective tissues like ligaments and tendons when people move their arms. But for the purposes of today's talk, I'm going to be fixing ideas and focusing on just one specific example. We're going to be looking at how blood flow through a diseased artery affects the formation of these structures called aneurysms. And we're going to be looking at how the blood flow affects the formation as well as the quantities that are related to the blood flow that influence the growth of aneurysms. So in that context, I'm going to start with an overview of the biology to briefly describe what an aneurysm is. And I'm going to talk about some quantities that people hypothesize are related or influence their growth and their sort of potentially eventual rupture. And then we're going to step through the mathematics that we use to not only solve the fluid flow equations, but to also keep into account that we care about certain quantities. And I'm going to describe the central aspect of this work, which is essentially error controlling these, let me do that. Error controlling these equations such that the quantities that we care about are accurately calculated. And finally, I'm going to talk about some interesting things that pop out when we apply this to this current problem, when we apply this mathematics to this current problem of interest. So, as I just said, we're interested in figuring out how the fluid flow affects the formation of these structures called aneurysms. And now aneurysms are these bulbous structures that are formed on what is a diseased artery. They come in two forms. One is a saccular aneurysm, and another is called a fusiform aneurysm. One looks sort of like a sac, the other one looks like a spindle. Now, these structures are a little weaker than the rest of the artery. So you have a reasonably stiff artery, which is like a pipe for the most part. And you have a certain region that is weak. So what happens is because of the fluid flow and the fluid pressure, this section bulges over time. And this can happen to a small fraction of people. But what's scarier still is that at some point, if this ruptures, this process is fatal. So you can have an aneurysm, for instance, at the base of your neck, and the artery leads to your brain. And if you have an aneurysm that ruptures at some point, the blood supply to your brain is cut off in the next few moments, and you're dead. So it's a scary problem. But the good thing is, if we can sort of track this, and if we sort of know what's going to happen, and from the fluid flow, if we're able to figure out that an aneurysm is going to form, you can surgically remove an aneurysm, or at least prevent its ill effects from happening. So, there are a couple of hypotheses that relate to how these aneurysms form, and I put them down in words. But in order to understand what they mean, we need to look a little closer at the inner wall of an artery. So an artery is essentially like a tube. It consists of what is called smooth muscle cells that line the tube. So this passive set of cells that line the tube, they form a tube. Now inside these smooth muscle cells, you have these things called endothelial cells, which are shown in two figures. So there are a bunch of endothelial cells here. This is one endothelial cell here. And these endothelial cells are very interesting. So they can respond to both chemical factors as well as mechanical factors and do some pretty interesting things. For one, they can do something called, they can signal something called apoptosis, which is the programmed death of neighboring cells. They can do something called remodeling, which essentially takes the cells in the neighborhood and arranges them a certain way. And the way the cells are arranged in the neighborhood has implications for the strength of your artery. And finally, they can affect the contractility of your artery. So if you have an artery which is a tube again, you can sort of the endothelial cells can control how much the artery wants to constrict inwards. So the endothelial cells are interesting quantities. They can respond to mechanical forces and chemical forces, and we're going to be focusing on the kinds of mechanical forces that these endothelial cells respond to. So now, I'd like you to imagine a tube again, and you have fluid flow through the tube. Now, if you were to imagine a layer of fluid that's really close to the surface of your tube, it's going to sort of rub along the top surface or the bottom surface or the surface everywhere. And there is a frictional force at that surface, and that is along the direction of the blood flow. So if you have blood flow, you have a layer of cells, you're going to have a frictional force along the direction of the blood flow, which is what I call a shear force or a shear stress. And then stress is just a force divided by an area, so I'm going to use those terms interchangeably. And secondarily, you have the pressure in a pipe against. You have a pipe and you have a fluid pressure, and because of the pressure in the fluid, it's going to push outwards on the tube in equal amounts in every direction, everywhere. It's going to tend to make your pipe expand. So if you have a pipe and you're going to pump fluid in from both directions, for instance, at a certain pressure, the pipe is going to expand. So these endothelial cells sense both of these. They can sense both the frictional forces that come about from the fact that the fluid is flowing against or along the surfaces. They also sense the normal pressure, but they actually end up sensing the stretch. So you have a normal pressure, which is like a sort of blowing up a balloon. You have a pressure in every direction, and the balloon surface stretches everywhere. So the endothelial cells which line the surface sense that stretch. So now the sentence might begin to make a little bit more sense. Shear stresses drives apoptotic behavior of muscle cells. So the endothelial cells sense the shear forces, and they program the muscle cells to die or not. And secondarily, the cells remodel arterial walls under constant tension. So because of the tension of the surface, imagine your balloon being expanded, is being blown up again. Because of the tension of the surface, the cells respond to that, and they remodel the arterial walls. And by remodel, I just mean that they rearrange the way the cells are arranged there, which has implications again for the strength of the artery. So these two quantities are important. The normal stress and the shear stress are two quantities that the endothelial cells sense, and they manifest themselves in the aneurysm. The thing is, for a healthy human being, and if you have the normal blood flow going through an artery, the endothelial cells respond the right way, and they program the cells to do the right things. However, if you have some disruptions in the blood flow, it is believed that the signals that the endothelial cells receive are now disrupted, so they program the cells to do the wrong things, and we believe that the formation of aneurysm is one of those wrong things. So, we're interested in solving not only some fluid flow equations, we're interested not only in solving some fluid flow equations, but we're also interested in particular in making sure that our solutions are accurate with respect to certain quantities that we really care about. So, I'm going to take a bunch of detours during this talk. This is the first one for people who are not computational scientists. Or I'll do that a little later. What we really want to do is we want to solve a bunch of equations describing the flow. And in this case, I have a set of equations here. It's called these Stokes equations. But while they may look scary, this is a very simple set of equations. They relate what is called a velocity and a pressure of the fluid with an external force. So this contains two bits of information. It's Newton's second law of motion, if you remember from high school, and it contains the balance of mass, or like continuity of matter. Now, under normal circumstances, we would want to solve an equation like this. We don't do that. We write it in an abstract form or the weak form, and we can end up solving that instead. So in an abstract form, any equation describing any kind of phenomena can be written in some sense as I've shown on the right, which is essentially something like a function which depends upon the variables you care about equals some function of an exterior driving force. So if you remember Newton's second law, it's something like the rate of change of momentum of a body is equal to the external force applied, if you remember from high school. Even that relationship can be written in this form. A lot of relationships can be written in this form. So we have a PDE, or a set of differential equations that can be written in this form. This is where I'm going to go into detail one now. Under normal circumstances, the equation set that we get here is too complicated to solve in a continuous sense. So as a computational scientist, we come up with what is called a discretized method. In this case, we use the finite element method to solve it. But these discretized methods don't solve this everywhere in a domain. So if you have an aneurysm, we don't solve it all over the aneurysm. We solve it only at discrete points. So we get some answer. But what we're going to do instead here is to not stop at that point. We're going to say that we are not only interested in the solution of the fluid flow problem, but we also care about the shear or normal stresses, whatever they may be, because those are important for the endothelial cells, which is important for the aneurysm growth. So we say, all right, if you know the sign, it's an integral sign of a shear stress. So we say, we really care about the integral of the shear stress over the aneurysm surface, or the summation of the shear stress over the aneurysm surface. So what we end up doing is we use information from our abstract problem. We use information from the quantities that we care about, which in our case is the shear stress, and we construct an auxiliary problem. This is the critical step. We use information from the auxiliary problem and our primal problem to construct something called an error indicator. And now I'm going to break into my second detour for computation scientists, so non-computation scientists. So, like I said earlier, we don't solve the actual differential equations that we want to solve. What we end up doing is solving a discretized set of equations. So we have an exact set of equations that we want to solve. We have a discrete set of equations that we're actually solving. Now, we don't know the answer to the actual problem. We're solving a discrete set of equations, and we would like to know how off we might be. So this is a pretty cool thing. We're solving a problem that's not the original problem. We get some answer. And without knowing the actual answer, I would like to gauge how wrong I might be by making this approximation. So that's what I'm trying to do here. So I'm saying, for instance, this is the shear and normal stress that's calculated, which is denoted by the H's, it doesn't matter. That's the actual shear stress. And I'm saying it's a bunch of things. And in words, this basically says that the errors that you're going to see in the process of solving this problem depends upon how well posed your original problem is, how smooth your original problem is, and some information regarding the quantities that you care about. So we have a scheme to determine how incorrect your approximate answer might be. So what does this mean for our problem? So if you were to imagine your aneurysm again, which is essentially an artery, which is a tube with a little bulbous region. If you were to set up a simple, let's say a pressure gradient, so if you had a pressure at one end, let's say 5, and a pressure at another end, let's say 2, you're going to have a fluid flow that's set up. This would happen in a pipe in your home. You have a fluid flow that's set up. So let's assume that it's going from left to right. Okay? You have a flow pressure here, and pressure here, and the fluid's going to go. What ends up happening is because you have a primary flow in this direction, you set up a sort of counterclockwise flow in the aneurysm region. So you have a flow, and that drives another flow. And if you were to consider the shear stress at the aneurysm, which is what we care about, I've denoted them with these little cone arrow things, and you can see the counterclockwise cones, which are essentially the shear force. So you have a flow, you have a counterclockwise flow, and the counterclockwise flow has a shear stress on the aneurysm. Great. Under normal circumstances, as a computational scientist, you would stop your calculation at this point. You would say, I have a flow field, I've calculated shear stress, I'm going to report those results, and I'm done. But we don't stop at that point. What we end up doing is we say, let's construct this dual problem, which contains information about what we want. And we solve that as well. So that results in a flow field that looks, I'm going to call it a flow field, but it's not really. It results in a flow field that looks like this, which contains, which looks just like a flow that's driven by the shear force. Can you see these arrows? If you just had a bunch of fluid here and you sort of push them, you would end up with something like that. Great. So we use these two bits of information and we construct the errors. So we say we have all the information we need now to approximate what the error might be. And now I come to detour number 3. We use the finite element method to solve these equations. And it turns out that the finite element method is what is called a consistent method. So what this means is that if you increase the number of nodes at a point, so you're actually calculating a discrete set of points, right? If you increase the number of points you're actually performing this calculation, the more correct you'll be. So we use this error information and make those regions more dense. We just say we're going to have more points wherever we think the answer is going to go off, and we improve the accuracy of our answer. And yes, so I had something like to say there, but there are some other interesting things that pop out of it. If you really think about the first thing the problem that I described and the answer that I got, it's actually quite intuitive. If you want an accurate answer in this region, probably best to add more nodes in that region. It seems quite reasonable, but I told you that my scheme is such that it's more accurate where there are more nodes. But what is cool is that if you have, if you're optimizing not for the shear forces, but for normal forces instead, you end up with a different result. It says that you have to refine the mesh at the inlet and outlet, which is slightly counterintuitive. But if you really think about it, if you had a tube again and you had pressure at both ends, the pressure of the fluid in the tube depends almost entirely on just the pressure at both ends. And that's what this is telling you. So in summary, I'm just going to close and say that we have an abstract scheme that is capable of giving you a goal-oriented error control method for all sorts of differential equations. In particular, when you apply to problems like these, you end up with surprising results, sometimes not particularly intuitive, and it is useful for a lot of computational scientists. And thank you, and at this point, I'd like to open the floor for questions.
I would like to have some idea about the flows more than
Yes.
inside of this vein, or I think
It's an artery, but yeah.
On the artery.
It doesn't
Yes.
matter.
It was on the slide number 5.
Yeah.
So the blue color is representing actually the speed.
Yeah, there are two sets. Okay, there are two sets of information here. So that's why I didn't have two sets of arrows. I'm sorry. The color denotes the magnitude of the velocity. So this is, just imagine fluid flow through a pipe. It's got a standard parabolic profile. It's highest towards the center, and it's no slip at the two edges.
Yes.
Right?
So this scale of colors is in a meter per second.
Yeah, it's meter per second, but it's again unitless. I'm like a mathematics person, so it can be scaled up or down. I'm working with Stokes equations in that case. It's essentially dimensionless, but yes, you can think of it as meters per second.
Okay.
Yeah. You can add constants and make them. You can scale them up to what you want. Yes.
I wonder, is there any method to validate or find something?
Yes.
Well, after you solve
Yes. So you can. Yes. What you do is you solve the problem for problems with known analytical solutions. So this is a slightly complicated geometry, not as complicated as what you showed, but it's still not simple. So what happens is you can pick a simple thing like a unit square. You can say a square of side 1, and you can have a simple flow equation, and you can derive on paper what the answer should be. And then not finite element, a sort of classical analytical solution at every point, everywhere, a continuous solution. It's not a discrete solution. And then you can check your finite element method with that solution.
Okay, but for a patient, because that's for
Yes,
this,
so there are two steps here. So there are two modeling steps. First of all, these equations are very simplified. You have two steps. You have to model the actual physical system with a set of, in this case, differential equations that accurately describe any body first. You got to solve a complex problem on a sophisticated geometry to specify it to one person. So there are two problems here. I'm working on the second half. The accurate modeling question is a different question, but yes, that's done a little bit more experimental information. Yes.
Okay, let's go ahead and move to the critiquing phase. What do you think? I think Harsh did well in this talk.
It's very convincing.
Yeah.
You seem like you really know, you're really sure of what you found and what you're doing. You seem like 100% sure that I know that what I've done is right and I believe in it.
Yeah, which I do.
So it's, it really shows. And your voice is very, it varies, it's enthusiastic, that's really good. And I like the slides. I think they're good with the different images and the way you go through them.
Yeah, I agree. You had a very good energy. You moved. You were enthusiastic and nice slides. And I think also you explained the story.
Yes.
I agree with those two. And also, I liked your short and precise introduction, and that you moved on to your motivation, and you were clear about the motivation. And, yeah. I liked it.
Okay. Thank you.
I thought it was real nice when you explained the equations, just trying to make connections for us. This is Newton's second law and those kinds of things. And that's something, I wrote down professorial. In the sense that I think, and it's not that that's uppity or anything, but I think people who teach for a long time adopt that. And you already seem to have incorporated it. so I thought that
I mean,
was,
that was gathered over the last couple of, yesterday.
Yeah.
I mean,
Well-
the audience is diverse, so I figured
Yeah.
I'd throw those things in.
that you did, but it provide, and your voice was, as Heidi said, and Paulina said, I mean, your voice is really engaging to us, but it also provides real good emphasis on things. Yeah. Very nice, yeah, because Anna said, you cover the purpose well, and put the different medical devices, the different medical applications, I thought that was good. Opportunities for improvement. What do you think?
Yes.
First, I don't know, maybe you have that Alzheimer's references, I think,
Not on all slides, no. But,
or quite many.
no, not on any of them actually.
Yeah, that's my opinion.
Yeah, but this is the only one that's not mine, I guess, so, yeah.
Okay, then.
There was one slide, extra,
thought-
all the stuff is my stuff, so.
Okay, then it's okay.
Yeah.
Then, I think you talked too fast, I don't know if
Okay.
you were stressed, but sometimes I
Yes,
just have
yes.
difficult to follow.
Yes.
And that was also happening when you would answer, when you got the first question.
Yes.
You were actually interrupting him before he said the question. And why I'm saying that too, because it happened to me also. And I think it's very important, and making a good impression is to listen before saying the answer. And I know you know or you're very good at what you are doing, and that's maybe why, but just listen until you have said the whole question.
As long, I would just say, and with the speed, I understand that some people have trouble following, but as long as I manage to follow, I like that I like the speed, because I was able to follow it, and then I feel like I kind of get enough flow through the whole talk. But of course, you have to know with the audience if you
I have to average it somehow.
something like that. I don't know. Make sure that people don't fall off, but still don't get too slow when you talk, and then it might be, for some people, it might get a bit dull.
I just have a couple of comments. I don't have any big picture things because I thought that you did well. By the way, I really like the slide, maybe it was the one before, but I don't want you to leave this one, but where you talked about the discretized equations and you explained the role that they had there, and that you didn't have an experimental set of solutions that you were going to compare against, but you were still trying to estimate the error.
Yes.
I thought that was, I thought that was just a big picture view of what it was you were doing, and I felt, wow, you kind of gave me this vista then on your work. On this slide, I read that headline 3 times, and I just don't know what it means. It doesn't.
Okay.
Yeah, and
Can I
so
explain that?
I would work on that, make it more concrete.
Okay.
That would be it. And then I think you had an image earlier on, maybe slide 3. Yeah, before. That one on the left, I just couldn't read the call outs. And
Okay.
so I wondered, are they needed? Because the one on the right, boy, I can read everything.
Yes.
And so the one on the left, I couldn't read it, I didn't know what to do with it.
Yes.
And so maybe, we borrow images from books and stuff, but maybe I might I might rethink it.
Yes.
It's going to be for here and mask and something.
Yes.
Hey, good work.
Thank you.
Really nice work. Way to go.